Okay, so today we'll have, again, we'll have 2 hours. Sorry, I need to still catch up with last week. And I will give you a break in between again, okay? Because I will pass to a different set of slides and I'll give you time to your mind. Let's put it this way. So yesterday we saw a little bit of a cup. And we started with alcohols and amines. Today we'll carry on with in the first part. I would like to do a little more of alkanes, alkenes, and alkynes. I would like to say probably the most useful ones that you need to consider today are the alkenes. It's a very versatile functional group. You can find it anywhere, or even if you don't use it, if you don't find it specifically in your molecule, you can place it doing a functional group interconversion. For instance, you can place alkenes and I use it, and then maybe, for instance, hydrogenate it if you needed a saturated one, or play with more chemistry around that. But probably of these 3 classes of hydrocarbons, alkenes are the one that I would like you to focus a little more. Yet alkanes and alkynes are still quite useful. Just to say, probably alkynes are the one that normally you make alkynes from other alkynes. It's more unlikely that you make alkynes in a different way. But you can use alkynes to produce more chemistry. We will see. Okay, so for instance, how do you make this one? There is a little bit, remember that yesterday we saw alcohols and amines. We will reuse them. They will come again. The idea is that by the end of this course, you see all the different functional groups and you map them immediately. You say, okay, I have an amino group, a carbonyl in this position, an aromatic in this other position, and you can have a good idea where to start with your disconnection. This one is easier. How do you do it? Where would you start? Which bond you disconnect? Start pointing. Okay, for instance, if this is carbon 1, 2, and 3, for instance, where do you cut? Clearly, be plausible. You're not going to destroy the aromatic ring. The aromatic ring stays as it is. That's a good start. The cyclohexane could be made, could be used as it is. There is not a very, unless it's specified at the exam, either I give you the starting materials or I can give you in the exam question something like, go back to benzene, go back to phenol, going back to a compound, which has a very common one is go back to a compound which has no more than 6 carbons and no more than 1 or 2 functional groups, so that you can be creative. I'm not dictating what is the starting material, but you can have freedom. Also, when I give you the starting materials, you have freedom. So normally the starting materials is a suggestion. But so where do we cut? 1, 2, 2, 3. Don't say 1, 3, please. Sorry.
There we go.
Too late. Exactly. You're going to say exactly this one.
I was going to put chlorine instead of bromine.
Very good. Very good, Rebecca. This is something that we saw in the first part of the course. Now, I know that it should be alkanes, alkynes, and alkenes, but again, I'm going to mix up everything. And remember something else. Again, all the chemistry they are going to use in this part of the course is something you already used in the past. I'm not going to teach anything new. I'm just going to recall the chemistry that you've done, only the organic chemistry that you've done in the first, second, and third year. Nothing more, nothing new. So we saw cross-coupling reactions in the very first part with me. This is a moment where it becomes very useful. When you see a structure like that connect to a benzene ring, you can always cut and think about starting from a cross-coupling reaction. Even if this one is a large part, as a larger part of the molecule, or this one as a larger part of the molecule, this specific bond can be done in synthesis very specifically, very selectively in that position. That's the very important part. That's the usefulness of the cross-coupling reactions. So whenever you see, especially if you see two benzene rings connected one to another, think about, I might want to start with a cross-coupling reaction, especially if that breaks the molecule in two, more or less in two. What happened? This one has started to sleep for sure. That's it. Sorry. So if you want to cut it, boronic acid, for instance, and bromobenzene in this case, that suggests Suzuki coupling. It's Suzuki because if you remember, the Suzuki is the one that you do with the boron. That doesn't mean that if you do any of the other couplings, it will be wrong. This is just an example. So in synthesis, you just get the boronic acid. You use a palladium 0 species, like you have done in the lab, and you can do that. How can you make the boronic acid? Do you remember? Because this one will have 6 carbon and 2 functional groups. So let's say that I'm asking you no more than 6 carbons, no more than 1 functional group. How can you make this one? We're going back to alkanes. We'll see. Remember at all, how do you produce boronic acids? We did that. If you don't remember, don't worry. But please try to remember at the exam if you need it. Normally, boronic acids can be produced by the corresponding halogen-alkane in the presence of boronic esters. From the boronic ester, you can then hydrolyze it and produce the corresponding boronic acid. But I will not ask you how do you introduce the boron, but I might ask you, where do you start from? What do you start from? And in this case, it's going to be the corresponding bromo. What about this one? Where do you think this compound can come from? What's the starting material to make this bromo hydroxyl? We didn't discuss too much one way to make alcohols, but this is probably a good moment to remind you. And anybody has an idea? What can we use to do that? Epoxide is good only when you have an open alcohol. Epoxide is always good when you have something to make it open. In theory, you can. If you had an epoxide here, you attack with a bromide, you will open in this position. It could be actually, it's doable. There is something easier, but it's doable. It's not a bad idea. You can have an alkene, and you need to hydrate the alkene. There is something easier, which I don't know. I don't have on my screen the structure that I used to put. So I don't know. But this is the good of the retrosynthesis. Epoxide, I never thought about using the epoxide in this one, but it's actually doable. An alkene and then do a hydration of the alkene is also doable. It's not the easiest reaction ever, but it's doable. What I will do here is probably remember the chemistry of the carbonyl. Chemistry, I keep saying that we will reuse over and over again the chemistry of the carbonyl. The carbonyl can be reduced down to alcohol as well. What I'll probably do here is reduction of the carbonyl. In retrosynthesis, you put the carbonyl, which is, yeah, what I thought I would do. So in synthesis, if you see that in synthesis, if you see an alcohol, it can always come from reduction with sodium borhydride, for instance, of a ketone. Then you need to place the bromide. Placing the bromide here shouldn't be that difficult. In this case, if the question was go back to a compound which has 6 carbon and 1 functional group, you got it, you stop here, you don't need to do anything else. If you want to surprise me and do also the synthesis of the cyclohexanone, please do. But you won't get any extra marks. That's the bad news. The good news is that if you mistake it, I'm not gonna remove any marks. So you can always do. I left this one on the video. How can we make this stuff? How can you make alkanes like that? So sometimes you think about alkanes, we don't use them too much, but look at some of the biomolecules that you find also in your body. Sometimes they're full of long aliphatic chains. Sometimes are full of long chains which have at some point some vitamins. If you look at the structure of vitamins, sometimes they're very long structures, often with double bonds inside in specific positions. But you can make them, and you can produce the double bonds in those specific positions. So how can you make this one? Any ideas? Let's say you have this comes from a fatty acid, which probably is hydrolyzed, and you end up with a corresponding fatty acid. So triglycerides, there are so many in nature that you can use. You can make biodiesel with this kind of stuff, which is quite cool. But how can you make the fatty acid if you want to make it? What I'm asking is basically how to make a carboxylic acid in that position. A good idea would be, we will see the VTIG when we do a little more of the alkenes, because the VTIG is one of the most important reactions to make alkenes, because it can be very selective. Let's say that you want to create longer structures, you can couple this one. You can have the double bond, reduce it down. You use a nitrile, use that. You get the nitrile instead of the bromide, and then you oxidize. You don't oxidize, you hydrolyze, sorry, the nitrile to corresponding carboxylic acid. So if you needed the carboxylic acid, this is a good way to make it. That's the synthesis. You want to see the retrosynthesis, go the opposite way. So from the main question, you should work probably from the bottom to the top. This is just a way to, if you want to create functional groups in retrosynthesis, you just need to remember, how can I make any of those? Another typical one, I don't know if you're gonna see it on an exercise, but I want to specify it. A good way to form benzoic acids instead, and this is also very selective, is this oxidation. What's the oxidant? Permanganate will do. Other strong oxidants will do as well. What I will use in the lab will definitely be permanganate because it's the easiest one to use. And you oxidize specifically the benzyl position. So if you use permanganate to oxidize any of those, it will not work as well. The permanganate works really, really well on the aromatic, on the methyl connected to aromatic, the benzylic position. This one doesn't work as well. But on a fatty acid, on a long chain, when you have aliphatics, you probably want to go for maybe hydrolysis of the nitrile or oxidation in other different ways. You have an aldehyde oxidation of the aldehyde. We will need to focus a lot on this one. That's really important for today. Okay. How can I make this one? Now, I really want to move as soon as possible to the double bonds because double bonds are too versatile, too useful for photosynthesis and synthesis. Whether you need a double bond or you just want to use the chemistry of the double bond, it's too important. So here, you said the aldehyde. Where the aldehyde, where the bromine? Sorry? Where the aldehyde, where the bromine? So here the aldehyde. Let's forget about the rest of the molecule now. How does it work? Wittig will do. Or there is another chance. Yes, Wittig will do. Grignard. Whenever you need, remember, if you see a double bond, you can imagine that it comes from the corresponding alcohol. And the corresponding alcohol might come from a Grignard. That's a good point, but Wittig is a good one. The only difference sometimes with the Wittig and the Grignard, when you have to choose whether to use a Wittig or a Grignard, is the geometry of the double bond. With the Wittig, you can dictate the geometry of the double bond if you want. With the Grignard, is more unlikely. You probably form the double bond, the more substituted double bond, the more stable double bonds in general. So normally, trans double bond more substituted are the one that forms more easily. With the Wittig, you can play with that. The good part of this one is it's also symmetrical. So again, whenever you see something which is symmetrical, so in this case, on the very first of the material, this is why I have to put the aldehyde here instead. But it is not wrong. What you did is not wrong. What is more difficult is that when you need to synthesize your cyanoaldehyde, that is far more difficult to synthesize than the correspondent with the bromide. But on the paper will do. So again, in this case, I will use the Wittig. Do you remember the Wittig? I think maybe Marcella did it. Do you remember how to create selectively single bonds or double bonds? Double bonds cis or trans with the Wittig. That's important because if you just say Wittig and you have the wrong conformation of the double bonds, that's a no. In that case, the exam will be wrong if you use the Wittig. Because depending on the highlight that you're going to use, you can have stabilized highlights. Highlights, I never know how to pronounce it exactly, but you know what I mean. Stabilize one, form cis or trans? Come on, it's 50-50. Who does? Think about from the stabilization point of view. If it's stable, it forms normally the most stable compound as well. If it's a stabilized highlight, phosphorus highlight, which bond do you think you form? Trans. And how to stabilize the halide? How can you make it more stable? When you put electron withdrawing groups on the halide. So the stronger the electron withdrawing nature of the compound, the more stabilized is the halide. If you stabilize the halide, you get a trans double bond selectively. An aliphatic chain. An aliphatic chain eventually with a phosphorus triphenylphosphine. This one will be unstabilized, and that will give you the cis. So if the double bond you want to create is cis, you must use this one. In this case, if you want to go via the Wittig, you must have the halide stabilized. In this case, I have to be honest, if you choose the Grignard, will work the same way because the Grignard will form the most stable double bond anyway. But think about the possibilities. If you have the trans, you can always use the Grignard. If you have the cis double bond, you can use the stabilized halide, or you can use something else. There is a variety of things that can give you cis. Not many, but there are other compounds that can give you selectively cis double bonds. With the synthesis. In this case, I've used a sort of normal one. And this is another example. Actually, whenever you use the normal highlight that you want to. If you are on the paper, I'm very happy. You don't have to say you need to use this one. It's just a variety to show you another potential starting material. Okay, so if you have this dihaldehyde with two equivalents of your phosphorus halide, you will get your molecule with the trans double bond selectively in this place in one pot. Okay. This is to remind you. Whenever you use the Wittig, remember to think about the structure of your highlight. Stabilize ones. Yes, you need to remember, but if you remember, stabilize, it means that it forms the most stable one. And what stabilizes the phosphorus is something which withdraws electrons. Electron withdrawing groups withdraw electrons, stabilize the halide, trans double bond. Something electrodonating, which is pushing electron, it destabilizes the halide, and then in turn give you this. This is very important for the photosynthesis point of view, because again, you need to tell me the conditions that you're going to use. Okay? Carry on. How do you make this one? Now we have a cis double bond. There are two, at least I can see easily two potential ways to do that. We discussed already the stabilized, in this case, unstabilized highlight. So I'm not going to allow you to use this unstabilized highlight. What would you use instead? I've used that in the video. If you watch the video, you should remember. If you didn't, you should remember anyway, because again, the chemistry that we're going to use now is something that you've already seen for sure. I hope. Proud. Anything? Any ideas? Okay, clearly you can use the unstabilized halide, but that would be too easy. Do you remember anything else that gives you specifically the cis double bond? That comes very, very useful because it's very specific. If I tell you that I can start with an alkyne, does it help? How can you make double bond? Dehydration, Wittig, any kind of Grignard because of the dehydration. But you can also make double bonds clearly by reducing triple bonds. There is one specific compound that when you reduce the triple bond gives you selectively cis bonds. One of the options is, if you don't remember, Lindblad catalyst. Poisoned, reducing catalyst. When you poison the Lindblad catalyst with barium sulfate, as far as I remember, but there are other poisons, you can selectively, since it happens on the surface, since you have your alkyne on the surface of the catalyst, when that happens, when you go for the hydrogenation, the reduction of the alkyne is clearly a hydrogenation of the triple bond. When it happens, if it can happen in the surface, think about the same way as you do periplanar, pericyclic reaction from the suprafacial point of view. It happens on one phase only. When your alkyne sits on the poison catalyst, it clicks so that it forms only the cis compound. From the mechanism point of view, you don't care. I will never ask you the mechanism. But please remember that's a good way to do cis double bonds. So here we have different options. I said, okay, if you break the double bond, you can have the Wittig, like we were saying. If you, in this case, if you have to choose where to put the phosphorus, where to create the halide, and where to create the aldehyde, you need to put the highlights on the saturated version of the compound because it has to be unstabilized if you want to get the cis. Then this one can come from, for example, we saw that yesterday, it can come from, for example, this reaction. Otherwise, that's what I mean. You do an FGI, you transform your double bond into a triple bond. Then, well, this is carry on doing the retrosynthesis. But this is the important step here. In synthesis with this one, you need to use the Lindblad. And the rest of the molecule, again, this one, remember, any chains which are H2, H2, OH, can always come from an epoxide. It's a very easy way to create an alcohol. Only you need to have two consequent methylene groups and then your alcohol. Then you can do your reaction. Otherwise, if the alcohol has only one CH2, it must come from a different reaction. That's another option, which also involves having the cis double bond already in place. And what's the synthesis of this one? In synthesis to create this one, to create your target molecule of these two reagents. That's easy. You have a bromide and a carbonide. Grignard. It's just that. If you have anything which doesn't have a good living group, and the aldehyde, formaldehyde, definitely has two hydrides, horrible living groups. That makes your alcohol. Formaldehyde gives you primary alcohol. But then again, we'll focus on the forward synthesis. Pathway A, the red one. Let's do the forward synthesis. You get your unstabilized halide. You attack your carbonyl. It's very selective. The fact that it's unstabilized, because it has all electrons which are pushed towards the phosphorus, which makes it unstable, creates your cis double bond. If you use the non-stabilized, we'll give you the Z. If you use the stabilized one, gives you the E, of course. So remember that. I don't know if I have time or if I want to tell you about the reaction with the aldehyde and the epoxide. So it's not that trivial. Let's see if someone spots it in 1 minute. How can you use the aldehyde and the epoxide to create your compound, your alcohol? So basically, you need to form this one. It's not that trivial. What's the nucleophile and what's the electrophile of the two starting materials, the epoxide and the aldehyde? But is the aldehyde a good nucleophile or not? The enolate of that, of the formaldehyde, is not very useful. But there is something you can do on the aldehyde. You remember anything that turns the carbonyl, which is normally electrophilic, into something which is actually nucleophilic? Ampolon chemistry. Do you remember how to do that? Of course, it's ampolon, because the carbonyl is normally an electrophile. You want to turn it into a nucleophile. Remember what to do. Normally, what you want to do is you treat with ditiols, for instance. I'll go here and then I'll cancel it. Form your heterocycle here with the proton. You can use Bewley. It takes out one of these protons and create a negative charge here. Okay, I'm not gonna do step by step. Then once you use your Bewley, you take one of these protons, which are fairly acidic, very acidic, but Bewley is a strong base. So it's all relative. Then you can use your reaction with the epoxide. Your negative charge attacks here. This one opens. You get your alcohol. You deprotect the thiol doing mild acidic hydrolysis, and you get your molecule. Okay, ampolon chemistry. I will try to use, it's like, this is one of the reactions that I will try to avoid if it's possible, if there is another way. But if you remember that and you know how to use it, it's very useful. I will try to avoid it as much as I will try to avoid nucleophilic aromatic substitution. But again, nucleophilic aromatic substitution is absolutely doable. If you want to do it either via diazonium or via benzene or via additional elimination, there are compounds. You need to know, that depends strongly on what is the rest of the molecule, of course. You cannot use it anytime you want, but it's doable. The same is for the ampolong. You're adding 2, 3 extra steps with potential byproducts and potential problems. So if you can avoid it, probably I will avoid it. But if you do it on the paper, that's absolutely doable. That will be perfect marks. Although there might be something which is much easier and faster. Yeah. Mild acidic hydrolysis is one the same as you do the deprotection of the diols. Thiols and diols are deprotected in the same way. Don't confuse with the Corey-Seebach when you remove it to saturate that bond. If you do mild hydrolysis, you go back to carbonyl. If you do Raney-Nichols reduction, you turn that one into the corresponding saturated version, so with the CH2. In this case, you want to keep the carbonyl. So this is what you'll do. Ampolong, you spot it quickly enough. Well done. B. We said that. Well, we didn't talk about this particular, the start of this reaction, but you have acetylene. You need a very strong base because the protons of the acetylene are more acidic than alkanes, but yet they're not that acidic. So you need a very strong base to take one of these protons. And then with an ion version of the alkyne, you can do SN2 here. This is what you want to remember. If you do have a cis double bond, think about maybe you can use the Lindlar catalyst, or you can use the Wittig with the non-stabilized halide. There are not many other options. There are other catalysts, different poisons, because you normally poison with barium sulfate, but I can show you, yeah, lead sulfate, other poisons, as long as they make the palladium over carbon that you normally use for hydrogenation a little less reactive, plus the surface of the catalyst has these defects and poisons that makes it sticking to the surface and creating selectively just a cis double bond.
If we just wrote Lindlar catalyst, would you be happy with that?
I would be happy with that. I will be happy with that because when you do retrosynthesis, my aim for retrosynthesis is like if you were in a lab and you have a molecule to synthesize and you have that double bond and you think, okay, I remember I can use the Lindlar catalyst. In that case, if you don't remember exactly what it is, you go back to the literature and you have a look at it. But only the fact that you remember that you can use it is good to me.
What do you mean when you say
Because the palladium over carbon, or sometimes palladium over carbonate, it especially depends on how many atmosphere of hydrogen you're using. It can oversaturate everything. So you can go back to the corresponding aliphatic version. Instead, you want to stop to the alkene. That one plus the fact that everything happens on the surface gives you the cis double bond. But the poison mainly is needed to slow down the reaction and prevent that it saturates everything. Okay. Let's say this one. I need to split evenly enough the two parts of the lecture in this one and when we're going to use cyclizations and heterocycles. This one is the opposite. If you want, this is the synthesis. If you want, say it backward. If you are too used to retrosynthesis now because you're getting proficient in retrosynthesis, say it from here to that. Try to spot what you can put here and what you can put there. Again, the aim of the lecture is alkanes, alkynes, and alkenes, but I like to mix functional groups because in the end, you're going to have big molecules with so many functional groups that you have to decide where to attack. Sometimes happens that I give you this kind of exercise. Let's say that we were discussing yesterday. I give you that target molecule and I tell you that the alkyne is one of the potential starting materials. Any ideas? Where do we start? Starting from the retrosynthesis point of view. So I think it's easier. What happens first? If you need to disconnect anything on this target molecule, where do you start from? Which bond? I'll give you numbers. This one, 1, 2, 3, and 4. Which bond you break? 2, 3. Why?
Because I want to make it out.
Fair enough. This is a lactone. How do you make lactones normally? Cyclizations of an alcohol and a carboxylic acid. Well done. Then you have this becomes more difficult. So now let's say that this is here. Anyone? Or you can start from the alkyne. Anyone? Please. Yeah. I don't know. Technically, probably you can do it. I don't know how easy it's going to be in the synthesis. What I will do normally, if you have many functional groups, try to do an FGI and turn something which is super reactive in something which is more inert. And you can make it reactive only at the moment that you want. For instance, you turn the carboxylic acid into something else. Remember, you turn it in retrosynthesis. It means that you start from the other compound, which is going to be a carboxylic acid in the end. Let's analyze it all. So, opening of the lactone was, of course, a very good option. Since you have to start from the alkyne, you need to place the alkyne somewhere at some point. So you do a functional group interconversion, and you turn it into the alkyne. Now, on this one, if you look from the retrosynthesis point of view. If you have something like that, you want to place the carboxylic acid in the moment that you really need. A very good way is like for the Grignard. You can use the Grignard or you can use a Bewley. But whatever happens, you can use the Bewley and CO2. Bewley to take this proton, like you'll do with the Grignard, and then you bubble CO2 and you get your carboxylic acid. If you want to create carboxylic acid, it's always a good option. Either Grignard or organolithium, organomagnesium or organolithium, and you bubble CO2 selectively. You make selectively the carboxylic acid in that specific position. It works extremely well with aromatics, but it works with others too. Then whether you choose Grignard or organolithium, it's your choice. They both work. This is the reaction that you need to do if you want to use the alkyne. Because of course here, you need something like another very strong base. It could be another Bewley. Be careful, I don't know, because the Bewley probably, I don't know, Bewley with acetylene might take both protons. The sodium might probably take only one. So you need to take only one proton here to attack the Grignard, the carbonyl. So if you take one proton here, the negative charge will attack the carbonyl here and form your alcohol. On top of my head, I will say, I don't know. Probably sodium hydride. There is a good chance that sodium hydride might take both, or it gives you a mixture on this. Sodium amide, and the amide with the sodium attached is quite a strong base. It wants to become ammonium more than say as it is, but the sodium hydride is probably stronger. It may work. Top of my head, I will say that you are in the either you go back to the literature and see what people did, or that will be your job in the lab. Or you have both options, you try them both and see the one that gives you the best yield. Top of my head, I would say they probably will use the amide for this reaction instead of the hydride. But I'm not saying that the hydride will not work.
Did you theoretically use like a computational method to see which was best?
Computational method, probably, yes. I would say that you can use computational method for anything. But probably having a good look at the pKa's in table might save you a lot of modeling time. Maybe this is not a reaction that might require such a strong computational background. Maybe just going for the literature or going for pKa tables and see which pKa you need to do that might help. Instead of, it will save you time and money in modeling, but computational method works for everything. So it's always good to think about from the theoretical point of view. And you have the alkyne at this point. You hydrogenate. You need to create the trans double bond, so not the Lindlar in this case. Especially because you need to hydrogenate even more. And that was one of the reasons why the Lindlar works so well. So you need to do hydrogenation twice because you need to go from the triple bond completely saturated. Only at this point, you can do the first reaction that you, of course, suggested, ring opening of the lacton. In this case, it's going to be the final reaction, ring closure. In this case, activating a little bit the carbonyl makes this alcohol nucleophilic enough to form a 5-member ring. A 5-member ring, kinetically and thermodynamically, is very easy to form. Then you got your molecule. But the good reasoning was really starting from Again, alcohol on one side, carboxylic acid on the other. If you want to refresh any hydrogenation conditions when you get something, or for instance, when you use reducing agents instead of hydrogen itself, some reducing agents specifically give you reduced, I don't know, the carbonyl to, for instance, sodium borohydride, reduce the carbonyl to alcohol, but it stops there. Lithium aluminum hydride, if you push, you can even get the saturated version. You use, we have seen the, we have seen yesterday the reductive amination. One of the specific compounds, reducing agents that you use for reductive amination is sodium cyanoborohydride, because it's an even milder hydride than these others. In that case, it quite work very specifically to reduce that amine to saturated amine. If you want to refresh it, either from old notes, books, this website as well. Helps a lot. Other uses of alkynes. And then probably we'll stop. You remember oxymercuration, demercuration of the alkenes. You might have done it the first year when we started talking about alcohols. This one on the triple bond works more or less in the same way, but instead of getting the alcohol, you get the enol, and you get the enol, it turns automatically into the carbonyl compound. So the same mechanism of the oxymercuration, demercuration of alkenes works on triple bonds instead. This is one of the reactions why the alkynes are so useful. Instead of doing the alkenes and you create the alcohol, you do on the alkyne and you create the ketone. But the mechanism is the same. So again, I'd like you to focus from this point of view to this one. So again, in this case, this part of the lecture was partly on alkynes. In this case, yes, you want to create a carbonyl, which, as we know, is one of the most versatile, probably the most versatile functional group ever in organic chemistry. You can create a carbonyl starting from the alkyne. Sometimes it helps. In specific questions, it might really help. Let's say that you have, like you had before, a linear structure, but you want to start from the alkyne because it's easier. You do the reaction of the alkyne and then you hydrogenate everything to the bond up to the aliphatic part. But you keep the carbonyl if you use just hydrogen. You can do reactions like that. And from the retrosynthesis point of view, again, the alkyne depends, the use of the alkyne strongly depends if you have both protons or one R group instead of one protons. If you have acetylene, you can do symmetrical reactions like this one, and then you can play with the alkyne at some point. Remember something else. Always take into account that the alcohols next to double bond conjugate with the triple bond. The triple bond is a double bond. So if you can do conjugation with a triple bond, eliminating a water molecule, it might do it. So if you treat this one in acidic conditions, maybe temperature, there's a good chance that you will have at least on one side a corresponding double bond conjugated with the triple. This is always something you want to keep in mind if you're having alcohols. Sometimes it's a useful reaction because you want to form a double bond. If you want to keep the alcohol to do some other chemistry on the alcohol, like something that we saw yesterday, then you need to be absolutely sure what are the reagents and conditions you're going to tell me. Because you say, yes, I cook everything. If you cook it, you eliminate water. I use a strong acid. If you use a strong acid, you might eliminate water. Be careful. If you can do the same reaction that you wanted to do on a base instead, that will keep the that will keep the alcohol too. Unless you're doing it 1CB, but this is another matter. The 1CB is another potential problem. I will give you, don't worry, I will give you all the I lost that. I will give you all the clean slides. I think I will stop here for 5 minutes, and the rest of the hour, then we will do some heterocycles and cyclizations. Sounds good? No complaints? Sounds good. How do you guys find this part of photosynthesis? Again, I'm not using anything which is completely new. Only sometimes you have to use everything in one pot. That's the most, this is the advanced part of the retrosynthesis, not anything weird, new on retrosynthesis. So now we're trying to treat all the functional groups as single group. Remember, we want to put them in the same pot, one influences the other. This is the most difficult part sometimes. Okay. How's it going so far? Want to slow down to do more exercises? That's the problem. That's the fun of retrosynthesis. The point is that retrosynthesis is organic chemistry at 360 degrees. So whatever you use in first year might be useful now. You don't remember that, but hopefully we reuse, for instance, lots of carbonyl chemistry that we started using the first year. We reuse it in the second. And we reuse, for instance, now we're going to see, we're going to reuse some of the heterocyclic chemistry that we've done massively in the second year. I know that there is something that you need to remember, but each topic you need to remember something. Physics, you need to remember. Mathematics, you need to remember. History, you need to remember. Chemistry, I think you can use your brain better than history, because in history or literature, you just need to remember. Unfortunately, yes, there is a lot of stuff that you need to remember as well. But I hope that if you got the basics, and again, the basics are nucleophiles and electrophiles, a highly reactive compound makes new reactions, makes new carbon bonds or carbon-oxygen bonds, but it can make a lot of other side reactions as well. So you need to play with the conditions. Chemistry is not the easiest, probably ever, because you need to remember and you need to use your brain. Anyway, there are a lot of exercises that I leave in class. Use the Warren, especially the disconnection approach from Warren, because it gives you both a little theory, but a lot of exercises. You reuse the notes. There is a whole chapter on the Claydon. If you ask me if it's going to be enough, the chapter on the Claydon on retrosynthesis, I will probably say no. But at least from the number of exercises point of view. But it's a start. You want to go through workshops again before the exam, please let me know. We'll do extra sessions on that. I'm always available to do extra sessions. Please don't do it 2 days before the exam. Not for me, for you. Because if you need really extra help on retrosynthesis 2 days before the exam, I'm afraid it's too late. So 2 days before exam, it could be some specific thing that you want to ask me or Marcella about my part of her part. If it's something massive, it might be too late. We can do it, but I don't know if it's going to be useful or not. So if you do anything in between, even during Christmas holidays, I'm available on Zoom because I'm hopefully going to be in Italy. But it wouldn't be the first time that I do sessions with someone during Christmas holidays. I'm always available. My suggestion is start practicing. Once you start practicing, you cannot believe how many things are recurrent. How many reactions are recurrent? You think you need to remember them all. Sometimes if you don't know one, you can get away through a different pathway and you use another reaction that sounds more familiar to you. Retrosynthesis, there are more than one correct. There is always more than one correct answer. It's plenty of wrong answers too. I'm sorry, but yes. Let's carry on with this one. We always said, if it's possible, start the disconnection from the carbon heteroatom. This is also true whenever you use heterocycles, but it's especially good if you're using open structures. In this case, for instance, you might want to use the chemistry of the sulfur. And again, there are a few things that you might want to remember from the sulfur. It stinks and it's a very good nucleophile. Not necessarily in this order. If you're in the lab, the fact that it stinks, believe me. But it's a very good nucleophile. It does excellent SN2 reactions like this one. If you have a structure like this one, disconnect from, even if you have 2, 3 different heteroatoms, try to spot the weakest carbon heteroatom bond, and this is where you want to start your disconnection. Because in the end, your first disconnection is your last step in synthesis. So it happens when you have all the rest of the molecule together. It has to be the easiest one to be formed. So you want to start from the easiest part. And in this case, for instance, this carbon-sulfur bond is the easiest one. You can argue that also this one is enough. If you ask me between the two of them, what is easiest, probably I will say the one that I chose, but maybe for a different reason. Not necessarily because of the intrinsic reactivity of the sulfur. In this case, this is more nucleophilic. This sulfur will be more nucleophilic than this one. Why? They are both very nucleophilic, happy enough to react. Any ideas why? Exactly. Same as all the other aromatic chemistry, which again is recurrent. You will reuse it. If the same nucleophile is connected to an aromatic ring, the aromatic ring withdraws electrons. It makes it less nucleophilic than an aliphatic one. In this case, yes, it's not the best because you have next 2 subsequents are 2 aromatic groups. So it could be arguable which one is the best nucleophile. But theoretically speaking, the aliphatic ones, and aliphatic, I mean there is a carbon, a saturated carbon in between, they're normally more nucleophilic than the straight aromatic ones. This one can be done with the thiourea method. I don't know if you've seen the thiourea method. Who did some sulfur chemistry? Marcella with you. She did, but I don't know if she did this one. Did you use the thiourea to substitute a thiol instead of a, let's say, a bromide? Don't know if it rings a bell. But whenever you need a thiol, you can start from the corresponding bromide. We will see probably later. I don't remember if I have it on another slide, but you can start with the bromide and you can use the thiourea. Anyway, bromide or chloride, any halogenoalkanes will do. Then remember that the halogenoalkane can come from the corresponding alcohol. Where does this corresponding alcohol come from, you think? You see that most of the stuff is recurring. You have an alcohol like that. Give me straight away a good reagent that forms this alcohol. Very high yield, super specifically. Most probably the easiest way to form alcohols, we said. Guys, don't be shy. Better mistake now than at the exam. Grignard. I don't know if someone whispered Grignard, I didn't hear it. But whenever you have a Grignard, a carbonyl, which doesn't have a good leaving group, it forms the alcohol. In this case, will be super easy because you cannot even, it's between two tertiary carbons. It cannot, that water molecule cannot eliminate. So in this case, a Grignard will do, you can even mistreat this alcohol. It's very unlikely you're going to destroy it. The other option, again, we saw that before. If you start from a carbonyl and reduce down the carbonyl to alcohol, then you can have your alcohol then. Then you break here, for instance, and you do the typical, one of the easiest reactions you can do on the aromatic ring, one of the easiest electrophilic aromatic substitution, the Friedel-Crafts acylation. But if you started, if here you started from the bromide here and the corresponding aldehyde, or the other way around, the aldehyde here and the Grignard on the other side, that will do. You don't have the aldehyde. Remember that the aldehyde, please don't do like I've seen many times, don't do Friedel-Crafts with the aldehydes. Friedel-Crafts acylation with the aldehydes won't work. So whenever you have, whenever you want to keep a carbonyl, you need to have a good leaving group. So don't do Friedel-Crafts with the aldehyde. If you do this reaction with the aldehyde, you end up with the alcohol. Remember also that this stuff is also true. And you always need to consider when you have reactions on the aromatic ring. What other groups do I have? Where does that group orientate the next substituent. This is something crucial because if you have it in meta, then you need to change your strategy. Then this one, of course, comes with a simple SN2 reaction. Quickly, the synthesis. This one probably uses a base. Why do you think I might prefer using a base in this SN2? Think about what we discussed about that sulfur next to the aromatic group. It's like when you use the same reaction on the phenol. Very often, the two lone pairs of the phenol, of the oxygen on the phenol, are not nucleophilic enough. So you use a base to create the corresponding phenoxy. And this one is far more nucleophilic. The same is for the sulfur. It's slightly more nucleophilic than the phenol itself because the sulfur is more nucleophilic than the oxygen. But probably you need to use the base. Let's put it this way. If you do with the phenol, you must use the base. If you do with the thiol, if at the exam you forget to put the base, you might get away with that because I think sulfur might be nucleophilic enough to do SN2 also without the activation. It might, but if you do the base, it's not wrong. Friedel-Crafts acylation works nicely in para, probably very selectively in para. You might have a little bit of ortho, but the sulfur is a big atom. It hinders that position quite well. But in retrosynthesis, you don't care too much about ortho-para separations. You will just assume that you can separate. Then you reduce down this one to alcohol, let's say with sodium borohydride, and then remember some very good chlorinating agents, thionyl chloride, but you can also use, can you name other compounds that you can use to chlorinate something? If instead of using thionyl chloride, you use what? PCl3, phosphorus trichloride, phosphorus pentachloride as well. They all work. They're all quite good to substitute at some point in your reaction, your hydroxyl group with a chloride. Then you use a thiourea. I'm not gonna do too much the mechanism, although it's not a difficult one. But we don't care. Well, no, we don't care. I will never say I don't care about the mechanism. We are not focusing on the mechanism now. Retrosynthesis, we are not focused on the mechanism, but if you know the mechanism, you tend to remember the reaction. Anyway, the thiourea works extremely well to substitute that sulfur with the oxygen. So what's the? It sounds even stupid to say. What's the byproduct of the thiourea reaction with the thiol to create the thiol? What is more stable than the thiourea? This is more natural as well. The urea. Absolutely. Urea is more stable than the thiourea. So if it gives away the sulfur, it probably takes an oxygen. Okay, what do you remember about heterocycle formation on the second year? I will say, yay. As far as I remember, and I'm teaching that now the second year at this moment, I keep telling them heterocyclic chemistry. Everybody hates heterocyclic chemistry. I don't remember any of you on top of my head who tackle any of my questions on the heterocycle chemistry in the second year. I don't know why, because heterocycle chemistry is easy enough. It's all carbonyl chemistry. So carbonyl chemistry, at some point, you need to put an heteroatom. There are no many ways to put heteroatoms. And if you know the carbonyl chemistry, then at some point you will do it. But yet, I still cannot convince second-year students to appreciate how important is the heterocyclic chemistry. But it's all about carbonyl chemistry, formation of enolates. Remember, it's all a matter of what does enolize, what does not enolize. Then at some point you need to introduce the heteroatom. Probably the easiest way to put an heteroatom is now. If you need to put a nitrogen, you use a nitrogen source. It could be ammonia, which is not the easiest one that I will do in the lab, but it works. And again, carbonyl chemistry, carbonyl chemistry, carbonyl chemistry, carbonyl chemistry. I'm not gonna lie, if you know the carbonyl chemistry, you can do 80% of your retrosynthesis exam easily. You need to know what kind of carbonyl chemistry to use at the right moment. Carbonyl chemistry is quite vast, let's say. But again, carbonyl chemistry, carbonyl chemistry, carbonyl chemistry. Keep saying, I keep remember my colleague when I was doing the exam, wax off, wax on. Carbonyl off, carbonyl on, carbonyl off, carbonyl on. It's elegant? No, it's not. It works? Yes, it does. So if you want to do a reaction in 10 steps instead of 3, but it's fine doing carbonyl on and off, on and off, on and off, be my guest, you'll get exactly the same marks as someone who did it in 3 steps. Only I take a lot longer for marking your exam, and I will keep hating you for that. But I promise you I will be fair, and I will give you all the marks that you deserve. Anyway, apart from joking, anybody, I'm not gonna ask you, if you remember the name of this reaction to form eventually this kind of reaction. Normally I use this one to form pyrrole, but the chemistry is about the same. If it was a pyrrole, what would you call this reaction? Again, I will never ask you to remember a name, but if you do remember the name, it helps. This reaction is a Pal-Nord reaction. If you remember Pal-Nord, okay, think about the position of, I'm anticipating a little bit now, but I can show you how easily you reconnect everything to carbonyl chemistry. These carbonyls are in a 1,4 position. I don't know if you remember the relative position of the carbonyl really helps in the synthesis of your starting material, which includes the 1,4 dicarbonyl in this case. If you want to get aromatic 5-member rings via Pal-Nord-like reactions, you need to get a 1,4 dicarbonyl. Well, I don't want to anticipate too much. We will reuse 1,2, 1,3, 1,4, 1,5, up to 1,6 dicarbonyl relationships later on, because they're useful. Do you remember how to, I think we saw that already. Do you remember how to do the decarboxylation? If you needed this one as an activator of that position. We saw that. Yes, I did, yes. So why would you need this one? You need this one to selectively take only one proton. If it's in between 2 carbonyl groups, it's far more acidic. You don't have any possibilities that actually the base takes this one. you don't have any kinetic thermodynamic problem. It always gets this one of those is far more, they're far more acidic. So selectively get this one. So you use the ester group as an activator. You use the ester group as an activator because the ester group, you don't use another carbonyl. Also another carbonyl activates it. But if you use another carbonyl, let's say a ketone or an amide, even worse, or even if you use a ketone, then removing the ketone is far more difficult. Removing the ester at this level, it's easy. Remove the ketone, no. So you put this one as an activator, an ester group, take the proton, do your FN2 to form your 1,4 dicarbonate. The carboxylation. Because then eventually you need your furan, substituted furan. And if I just gave you at the beginning, this is the target molecule. You have a substituted furan. You have one substitute in ortho position to the oxygen, which is different from the other substituent on the other side of the oxygen. You don't start from the furan itself because you will never be selective. If you have anything like that, don't start with the furan thinking about at some point I will introduce the phenyl ring and another point I will introduce the methyl ring. No, you need to form it with the two phenyl and methyl substituents already in place because the furan is mildly reactive and you will have horrible mixture of compounds. Again, this comes from the reactivity of heterocycles that we done massively in the second year. But at this point, in a Paul-Knorr-like mechanism, protonation of this one attacks itself, elimination of water, furan. Any double bonds come from the elimination of water because of the previous attack on the carbonyl. The decarboxylation here, if you want to do straight from the ester, lithium chloride and the M2. If you tell me that your decarboxylation comes from the hydrolysis of the ester to form the carboxylic acid, followed by thermal decarboxylation, will do with me. I'm not gonna, okay, I'm gonna say it. If you just say decarboxylation at the exam will work with me. Just remember that you need to include the step of the decarboxylation. Even if you don't tell me what do you use to decarboxylate. If it was a second year question, I will ask you, yeah, but what would you use? Here, I just care. To me, it would be just fantastic that you remember that you need an activator to make your reaction far more selective. And then you need to decarboxylate it. That will do. If you don't put the activator and you need to do the same reaction, in the reagent state condition, in your forward synthesis, you need to specify what would you do for the either thermodynamic or kinetic control. So, as you prefer. If you want to use, if you are creative and you think I'm going to use the activator and then I'll remove it with the decarboxylation, that is the more elegant one to me. The less elegant and the more mixed in the lab will be kinetic thermodynamic versus thermodynamic control. If you need to take out the alpha protons on the thermodynamic side, you need to tell me the conditions. If you need to remove them with on the kinetic side, you also need to specify the exact conditions. Exact, I don't mean the exact minus 78 degrees, if you remember. If you say minus 80, I will accept it. If you say very low temperature, I will accept it too. But if you tell me I use B minus, that will not be enough, okay? In that case. In this case, if you put an activator, B minus, I don't care about what base you want to use. From LDA to hydroxide to hydride to a Grignard. Well, no, Grignard won't do because it will attack the carbonyl. Sorry, my bad. Any base that doesn't attack the carbonyl. But again, here I'm explaining both potential metals. This one takes out the ester group straight away by the carboxylation. This one is in 2 steps. It still works with me. And works in the lab, believe me. Remember that to decarboxylate this position, you must have a carbonide in beta. If you have a carboxylic acid and this one is an aliphatic group, this one will stay. It's not easy to decarboxylate this one. Other cyclizations. What do you remember about the deal solder? The deal solders are going to be good part of your exam in a way or another. Either because I'm asking specifically about the pericyclic reactions and the deal solder is a pericyclic reaction, or because you might want to use it for a retrosynthesis. Deal solder is one of those reactions that, like the cross-coupling reactions, it works specifically only with that, with the diene and with the dienophile. No matter what else is on the other side of each side of the molecule. If you have that diene and that dienophile at this point, they will join and form the cycle. It's like the cross-coupling. If you cut in that way, you put a bromide on one side and let's say a double bond or whatever else, depending on the cross-coupling reaction you're doing. On the other side, if you put palladium, only that part, only that side will join. So that's probably the easiest way to cut in retrosynthesis. The same is for a deal solder. What I like to emphasize is that sometimes you might want to place double bonds where even if the molecule, in the target molecule, there are not. If starting with a deal solder, nobody stops you from starting from a double bond and then say, and then I will reduce it down to aliphatic. But if you place a double bond wherever you need, so that you can identify a potential deal solder reaction, that in your molecule is going to be super specific, including stereospecific. This one, for instance. How do we do that? You have a saturated cycle. Nobody stops you from doing an FGI, a functional group interconversion, put a double bond somewhere, and that cyclohexane suddenly becomes a site for a potential deal solder. That's an easy one. You have this one, you say, yeah, but I cannot do deal solder with this one. Yeah, I put a double bond. Let's say that I do a functional group interconversion from your target molecule, which is going to be this one. You do a functional group interconversion either here or there. That depends. You move the 3 arrows in the typical way as a deal solder. You do a potential ideal retro deal solder. Is not a retro deal solder because in retrosynthesis, what you want to see at the end is just the synthesis. So is on the paper, on the retrosynthesis, retro deal solder. On the synthesis, is going to be a deal solder reaction. But for instance, let's say you put it here. You move the arrows. Remember the movement of 3 arrows on the deal solder. You break in 2 parts. Remember, and that's valid for all the other potential questions on the deal solder. The dienophile must have a good electrowithdrawing group to work well. If it doesn't have the electrowithdrawing group, it doesn't mean that it's not going to react, but you might need to push the conditions much more. But if the dienophile has a good electrowithdrawing group, the deal solder is facilitated. On the diene, it doesn't really matter. Going back to the first part of the deal solder, normally in your diene sits your HOMO, in your dienophile sits your LUMO. But now we don't care about the mechanism. You do care about the mechanism because it's going to be part of your exam, but not now. if you get that, forward synthesis, you do a very easy, very specific deal solder. You get your, therefore, nitro group with exact stereochemistry. And then you reduce everything down. You put a huge amount of hydrogen with palladium over carbon, not poisoned. So it goes straight to, it reduces down whatever it can. And then you get your amino group, plus you saturate your double bond. Of course, you are not going to saturate your aromatic ring because you need very, very high pressure and temperature to do that, because the aromatics are far more stable than normal double bonds. But in this case, it works. Be careful with the use of the FGIs, because putting the double bond here is an FGI, but also putting the nitro group. You want to start with the nitro group because having the amino here will deactivate the deal solder. So this is something that might indeed happen in your exam or in the lab. So you put a double bond, you think I can do deal solder, but then you end up with an electrodonating group on the dienophile. It doesn't work as well. So you want to turn the electro-withdrawing group, electrodonating group of the dienophile into an electro-withdrawing group. If you need an amino group, remember something, reducing down the nitro group, in synthesis to amino is super easy. The other way around is super difficult. So if you have if you ever have an amino group, if you want to turn into a nitro group, you need to introduce as a nitro group itself. Oxidizing, do this reaction in this direction is super difficult. So please don't do that. So again, FGIs, use all the FGIs that you need, that you might think you need. Same for carbonyl on and off, double bonds on and off. What you really need, from the strategy point of view, what you really need to be careful with is, what if I needed a nitro group? If you needed a nitro group and you have to reduce down this double bond, you need to use either something super specific that goes only on the double bond and it's not that easy, or you need to change your mind. Maybe the deal solder is not the best option in this case. Okay. I will have only, maybe only this exercise left. Because or whatever I leave, have a look at the slides, whatever I leave, use it for practice at home. Again, I will never, maybe there are more exercises that I can cover in class, but it's never going to be something which you didn't see already. It's just a different molecule with a different strategy. So that's not, we are starting to make something more, slightly more difficult. Where would you start? Remember all the basic rules of retrosynthesis. Let's not stop here. That's a good option. It's a very good option. I want to focus more on the part with the heteroatom and the stabilization. But from the strategy point of view, synthesis point of view, that's a very good option. Now let's focus on the other side. But that's a very good option. We said we have an aromatic ring plus another cycle. It can always come from a cross-coupling reaction. But let's focus on this part. Also, this one, I don't remember what did I do, but I don't think I will even disconnect this one at this moment. But you might see, you might tell me, hopefully straight away, where does it come from? Hopefully. So any idea, focusing on this part, on the right-hand side of the target molecule, where do you want to start? So here there are a couple of things that we can start doing. Consider I don't have the solution because I don't remember what did I put. It will appear, but consider what do we know about the retrosynthesis. Where do you want to start? Typical rule of the retrosynthesis, carbon-nitrogen bonds are easy to break. But probably they're even easier to break if instead of being a carbon-nitrogen, carbon with a saturated carbon-nitrogen bond, it's a carbonyl. This is one of the typical moments that you can put carbonyl off, carbonyl on. So for instance, yeah, this is exactly what I did. You put a carbonyl, but then in the end, you remove. Remember, if you want to remove this kind of carbonyls, either hydrogenation with palladium over carbon, pushing it a little bit, let's say higher pressure, or Wolff-Kishner or Clemenson. Those reactions that turn the carbonyl into the corresponding aliphatic. They are easy. Then you ring open. Remember, it's ring opening in retrosynthesis, it's going to be a ring closure. At the beginning of this lecture, we had a lactone. This one is a lactam. But chemistry works exactly the same way as we did before. Actually, it's even easier because the nitrogen is far more nucleophilic than the oxygen. So the lactam forms much more easily than the corresponding lactones. So you break this one. Now you need to probably, I will say that I will do something like a deal solder. I will try to spot a deal solder. You have a cycle 6. If you place one single double bond, which then can be reduced down, you can exploit that deal solder chemistry, which is specific, easy, on the way you want. So for instance, if you put a double bond here, remember that it's a retrosynthesis. So technically speaking, you can put the double bond wherever you need. Only you need to find the starting materials that eventually form the double bond there. Okay, that's the difference. But you can put the double bond wherever you need. Then in synthesis, you think about if it forms or not. But let's say you put it here. You do the typical 3-arrow movements. And you create your diene and your dienophile. This is a good dienophile. It has the nitro group on it, so that it activates the dienophile and makes the reaction easier. This one, I don't know if it's the right combination, but it's doable. Then you need to carry on doing the retrosynthesis of all the rest. The cis-nitro alkene will present a potential problem. Remember, you also need to form. You can put a double bond wherever you need, But again, you need to then form. You need to convince me that you can form the double bond exactly the same way and with the exact same stereochemistry. Let's put the double bond in another position. Again, you do the movement of the 3 arrows. This cis double bond might be easier. But again, you get the nitro. Actually, this one is super activated because you have the nitro and conjugated to it, you have a benzene ring. That's much more activated. This is already better than the top one for this reason. But especially you can do more chemistry. Okay, that is enough to form the diene. You do a simple Wittig reaction. This Wittig reaction, this one is a little withdrawing enough to form the trans double bond here. Everybody happy. Then you need to form this one. How? You need to form a cis double bond. What can you do? You cannot do, in this case, I'll give you a hint, you cannot cut and do a Wittig. You cannot play in this case with an unstabilized or a stabilized eyelid because in both sides you have electro-withdrawing groups. Electro-withdrawing groups stabilize the potential eyelid, and the stabilized eyelid will form the trans double bond. So you need to go through another route. Wittig is not an option here. That is the option. Since the Wittig is not an option, the Lindlar catalyst is always a good way, probably the easiest way to do a cis double bond, to specifically form a cis double bond only. The rest is chemistry of the alkynes, like I've seen before. You will need to remove this one and do, in this case, a nucleophilic aromatic substitution. I have one more review problem I will give you for home. It's not, this is just a synthesis. I will stop here.